In today's lesson, we're going to talk about angles on the unit circle. First, I want you to look at this angle that's drawn in standard position. Notice that the angle has the vertex at the origin, and one of the rays is situated on the positive x-axis. This is called our initial side. When you draw an angle in standard position, your rotation is counterclockwise, and the ray up here, this would be called the terminal side. So let's label that on our drawing. So we have the initial side and we have the terminal side. That's our angle in standard position. When you have coterminal angles, that's whenever you have two angles that are in standard position that have the same terminal side. So if we went this way and it was 120 degrees and went all the way around one full revolution plus another 120 degrees, the larger angle would be sitting on top of the other angle, and that would be a coterminal angle because the terminal side would be the same. Then the unit circle, the definition says that the circle whose radius is 1 unit and its center is at the origin of the coordinate plane. So all of our trigonometry is going to be built off of the unit circle concept when we start identifying all the functions, the periodic functions. And notice that the radius of that circle, where it got its name, unit, the radius is 1 unit. So we have a 1 unit radius to give the circle its name, unit circle, or 1 unit. In example 1, we're going to find the measure of the angles with the counterclockwise rotation. If this angle here is 45 degrees, then our positive angle is going to be 135 degrees because we've got to have 180 for a straight line minus that 45 is going to leave us with a 135 degree angle. So you notice that when we have a counterclockwise rotation, that's a positive angle. And starting at the initial side here on the x-axis, we go up and around. So a positive angle is moving up in that direction. A clockwise rotation, that's going to be starting with the initial side on the x-axis. When you go down, going down is going to give us a negative angle. And we've got 90 degrees plus another 30 degrees in a downward fashion. So this would be a negative 120 degree angle because we're 90 degrees down plus another 30 degrees around to give us the negative 120 degrees. So negative is the clockwise rotation and you're moving down from the initial side. One full rotation is 360 degrees. So in a quarter of a rotation, we would have 90 degrees, 360 divided by 4. In half of a rotation, that would be 180 degrees. And 3/4 of a rotation, that would be 270 degrees. And we'll get to know those terms as the quadrantal angles. They're lying on an axis at either 90, 180, or 270. In example 2, we want to graph some angles in standard position. So 85 degrees, we have the initial side on the x-axis, and we're going up for a positive angle and terminating 5 degrees away from the 90 degree mark. So that would look like an 85 degree angle. In B, we want negative rotation. So negative means we're going to go clockwise or down around. There's 180. 3/4 is 270, and we want 320. So negative 320 degree angle would look something like that in quadrant 1. 210 degrees, that was going to be a positive angle, and we said positive went up. Just like here, we could say 85 degrees was counterclockwise to give us a positive angle. Positive means we're going to go up from the initial side on the x-axis. So around 90, 180, and down in quadrant 3, we would have 210 degrees. And then for the last one, negative 135, so negative means that we're going down and from the initial side, and that was going to be a clockwise rotation. So starting with the initial side on the x-axis, going down 90, and then another 45 would put us in quadrant 3 for a negative 135 degree angle. Example 3, we're going to find coterminal angles. Our first angle, starting with the initial side on the x-axis, if we go counterclockwise 135 degrees and clockwise 225 degrees, the positive angle 135 and the negative angle 225, their net sum, the absolute value, adds up to be one full rotation. 225 and 135 is 360, so we have that full rotation. So whether you start on the initial side and go negative 225, or we start on the initial side and go positive 135, the terminal side of both angles will rest in the same spot. Find another way on part B. Find another angle that's coterminal with 198. So we could get two different results. One by adding 360. So 558 is coterminal to 198. And we can also go in the clockwise rotation and subtract 360. So negative 162 is also coterminal to 198. And then part C, are angles with measures 40 and 680 coterminal? So I would say no, because 40, starting out at 40, if we add 360, we're not to 680 yet. And if we add 360 more, that's 720, and 40 more, so that's 760. That's not coterminal. And if we try the alternate approach like part B and subtract 360, that's not enough. And subtract 360 more, and that's negative 680. So it's the right value, but in the wrong direction, the wrong sign. So 40 degrees, another way to think about it, 40 degrees is in quadrant 1, and 680 degrees is going to be in quadrant 3. So they are not coterminal angles. So angles on the unit circle, we're going to look at the two famous triangles from geometry, the 30, 60, 90 and the 45, 45, 90. Remember from geometry, the smaller side had the shortest measurement across from the smallest angle. So 30 had the relationship of 1 and square root of 3 and 2. Now, if you think about that from a unit circle, so we're talking about a 1 unit circle, we've got to force this hypotenuse to be a 1. So to do that, I can divide each term. If we divide the hypotenuse by 2 and the legs by 2, we're going to have the value on a circle whose radius is 1 unit. So let's get rid of this and think about that from the perspective of a 1 unit circle. Radius is 1. So the opposite the smallest angle is the leg, that's a half, and opposite the 60 degree angle, the leg will be square root of 3 over 2. And we had that relationship, x radical 3, and 2x back from our geometry days. Same thing with the 45, 45, 90. We had x and x radical 2 for our lengths. So if this length is 1 and this length is 1 and this length was square root of 2, and we divide everything by square root of 2, we're going to force this hypotenuse to be 1. And to force the hypotenuse to be 1, we're going to have 1 over the square root of 2 for legs, but we want to rationalize that denominator. So each of the legs would be radical 2 divided by 2. Radical 2 divided by 2. And in the image below that, you can see these triangles laid out for us here. So we have, this is our 30, 60, 90. So across from 30 is 1/2. For the y value, I'm writing it in the x coordinate. So this leg here is 1/2, and this leg out here on the x is square root of 3 over 2. On the 45, 45, 90, that would be this measurement here, and we have the same lengths for that triangle, so the legs are going to be radical 2 over 2, but because we're in quadrant 3, we're going left, which is negative, and down, which is negative. So this length here is negative square root of 2 over 2, and then we come down negative square root of 2 over 2. And our last triangle, that puts the 60 degree here, where we had the 30 degree here and the 60 here. On this triangle in quadrant 2, we have the 60 degree. So we're going to go left 1/2 and up radical 3 over 2. So negative 1/2 and then up radical 3 over 2. So that's going to be the basis for the unit circle, and later on we'll learn all of these values around the unit circle. The cosine and the sine of an angle and the tangent of an angle, we're going to look at. Theta is going to be the Greek letter that's used to represent the measure of an angle in standard position. And if we want to find the trig ratios of that angle, some angle theta in a right triangle, you might recall SOH-CAH-TOA as the mnemonic for sine, cosine, and tangent ratios. So the sine ratio is the length opposite our theta angle divided by the hypotenuse of the triangle. So opposite over hypotenuse is the ratio for the sine of the function. Cosine is going to be the length of the adjacent side divided by the hypotenuse. So adjacent divided by hypotenuse will give us the ratio for the cosine. And then lastly, tangent of a function is the opposite side length divided by the adjacent side length. So opposite over adjacent will give us the tangent ratio in a right triangle for our angle of interest, theta. In example 4, we want to draw the angle and then find the sine and the cosine of each angle. And 135 degrees, we just saw earlier that's over here in quadrant 2, 135, and it creates a right triangle with a 1 square root of 2 ratio, except the x-axis is -1 because we've gone to the left in quadrant 2. To get the cosine and the sine of the angle, the cosine of 135 would be the adjacent to the hypotenuse. So adjacent is -1 and the hypotenuse is radical 2, which gives us negative square root of 2 over 2. And the sine, since it's a 45, 45, 90 triangle, is going to be the same, just opposite over adjacent is going to be a positive square root of 2 over 2. On 150 degrees, we're looking still in quadrant 2. So 150 degrees is 30 degrees up from the x-axis in standard position. This angle here, that's our theta, is 30 degrees. So the ratio for our triangle is 1, radical 3, and 2. But our radical 3 is negative since it's going left on the x-axis. And the cosine of 150 is going to be adjacent divided by hypotenuse, where the sine is going to be opposite divided by hypotenuse. 120 degrees still in quadrant 2. 120 degrees would be here where the theta is 60 degrees. So our angle of interest is a 60-degree angle, which puts us square root of 3 on the y-axis and -1 on the x-axis, and radical 2 and just 2 on the hypotenuse, not radical 2. Don't want to make that mistake. So cosine of 120 degrees is adjacent to hypotenuse, and sine of 120 degrees is the length opposite our theta divided by the hypotenuse. And finally, for 30 degrees, in quadrant 1, our triangle is here. This is our theta of 30 degrees, and across from 30 is the length 1. The other leg is radical 3, and the hypotenuse is 2. So cosine of 30 is adjacent to hypotenuse, and the sine of 30 is opposite divided by hypotenuse. In example 5, we have find the exact values for cosine of -120 and sine of -120, and we're going to do that first by sketching the angle. So to draw -120 would be clockwise down here. And then we've got a reference triangle, so back to the x-axis where our perpendicular puts this angle at 60 degrees, since this is 120. To get back to the x-axis, that's called our reference angle. The length opposite 60 degrees is negative square root of 3. The length opposite the 30 degrees is -1, and the hypotenuse is 2. So we've drawn the triangle, we found the lengths of each side, and we can use the ratios. So the cosine of 120 degrees and cosine of 120 degrees -120 is adjacent to hypotenuse, and the sine of -120 is the length opposite divided by the hypotenuse. On example 6, I believe this is our last example, we want to use a calculator to find the decimal values for each of these. So -1/2, our decimal is going to be 0.5, -0.5. Square root of 2/2, negative, is going to be decimal 707, and negative square root of 3/2 is going to be decimal 866. So I point that out so that you can remember. You're going to see these values often when you're using a calculator, so you can remember what the exact values are. And cosine of -120, that's adjacent to hypotenuse. In the triangle above, we said that was -1/2, so our decimal is 0.5. Sine of -120 is opposite to hypotenuse. That's negative radical 3/2, which we already did up here, or negative 0.866. Cosine of 135 is adjacent to hypotenuse, and that's negative square root of 2/2, or negative 0.707. And finally, sine of 135 is opposite to hypotenuse, which is radical 2/2, and that's 0.707. So just using those basic triangles from geometry, the 30, 60, 90, and 45, 45, 90. And that's the end for lesson 2.